Thank you, Martin. Thank you very much. Vice Chancellor, DVCs, colleagues, guests, friends. It's an honor to be inaugurated into this professoriate here at NMMU, and I thank you for the trust. Thank you for coming. I'm especially grateful to have my colleague Martin here to introduce me. Very pleased to have my Greek family here to support me. And to thank you all very much for coming out, students in particular. So the role of the university in the society today is not a straightforward matter. We're struggling with a lot of things. Here in South Africa, the walls ring with terms like transformation, decolonization. But without wanting to minimize the role of our particular history here, anything but, in fact, these cries to me represent the channeling of rising global sentiment. And these two graphs from Thomas Piketty's recent book, Capitalism in the 21st Century, show a little bit about why. By the way, do we have a pointer here? Okay, well, on the left, these are two graphs that are basically showing the same thing. These are inequality levels through time from 1910 to 2010. For the Anglo-Saxon countries on the left, and on the right, emerging countries. And what we see here is that they all look more or less the same, these curves. Income inequality was high, it dropped, and then it rose again. And we're in the middle of this big rise at the moment. And as you can see, the rise happened at more or less the same time everywhere in the world. We're all under the same pressures. People in the world are unhappy. So for all our local problems, I feel this is one of the valuable roles of the university, is to allow us to sort of take a broader perspective and to look at what are some of the global currents, some of the bigger picture issues that are informing the social dynamics around us. And this talk is going to be a little bit about ways that we ought to perhaps be studying this problem. So, why we need a new approach. People here, as I've just mentioned, are very unhappy and it's getting worse. South Africa is another likely flashpoint. Places like, in addition to places like the Middle East and so on. According to increasing numbers of observers, we're approaching the end of a civilization. We really don't know what to expect. There's a lot of fear, a lot of uncertainty, and a lot of concern that other people are going to take what we have. And then we have the environmental problems, global warming, ocean acidification, global mass extinction of biota due to our activities, peak oil, dwindling fresh water supplies, overpopulation. Where does it all lead? And then it just seems that our psychological and social fabric has also become increasingly strained by the incredible pace of technological advance. And our inability to respond effectively to it in terms of the way we organize our economic lives, the way we deal with different communities and so on. So socially we are faced with these very awkward choices now, such as remain in poverty or develop but destroy the environment. Or encourage globalization to create jobs, but then suffer all the free market social consequences of fragmentation, family life, and so on. Or else, buck against that, go it alone, and invite the risk of ideological movements that may have antisocial consequences, as well as global economic backlashes from those in charge. So these are very complex problems, interconnected with one another, and they require transdisciplinary attention. So, in my view, this is how I, at least today, see to deal with these. Basically, make sure we do our very best to minimize human suffering now, not in the future, not in theory, and then learn and communicate to others how the world works, so that we may know the consequences of our actions. Repeat this process continuously, iteratively, because the one thing we know is that change is always assured. And we ought to bear in mind that how we see the world depends a lot on what we happen to be doing at the time, what we've been used to doing. So this is a bit of a dense picture here, and I'm just going to run through some of the traditional views that we who study the world around us, natural scientists and others, in fact, pretty much most people in Western civilization, these are the views that have shaped us, or sort of a summary of some of them. And then these are what I show in white, and then following that is my take on where science is starting to take us now. So one of the big tenets of science has been that things are composed of smaller things with more fundamental character. And if we understand those smaller things, and we know how they fit together, then we'll eventually understand the bigger ones, bigger issues. So the problem is that most natural and social systems that we deal with in everyday life around us are too complex for this rebuilding process. And they're really best studied as a whole. We just don't seem to be able to put those bits together using the laws of nature that we've discovered and come with anything that's really valuable. Now that's of course not true for many idealized systems, in particular in machines that we build and so on, but for human societies, for life, biological processes and so on, that's the case. Another view that we've had is this idea that we live in a sort of closed system, and these things tend towards equilibrium, an equilibrium state, or what we like to use a natural balance. It's the right thing, where no further change occurs unless something happens. But the truth is that most natural and social systems of interest don't behave like that, because they're open systems. They're open to exchange with their surroundings. And so equilibrium is really a temporary affair in a sea of constant change, which, as it turns out, is often discontinuous and goes and jumps rather than as a sort of a steady progression that we can easily get used to. Of course, Newton's ideas about nothing happens to an object unless a force acts on it. Definitely the case when we are modeling straightforward mechanical systems, but because of this case of objects existing continually interacting with their environment, there's always something going on. Mathematics, in particular analytical mathematics, is regarded as a language of nature, and it's been now our human fate, I suppose, to regard mathematical simplicity as an indication of correctness and of elegance and of great value. There are now indications that things are not as deterministic as we had imagined in many cases, and that the logic of nature may be more statistical rather than deterministic. And that we now are coming across many instances where uncertainty, and perhaps fundamental uncertainty, plays a role. So let me skip then to this idea that humans exist in but are distinct from their environment. And this is something that we are really discovering is not true in this era which we now call the Anthropocene, that all biological organisms, including humans, as well as their technologies, are really facets of environment, and they exist once again in continuous exchange, material exchange with this environment. on a number of time scales and spatial scales. Finally, sort of the idea of free will is something that certain sectors of the population are extremely insistent upon, that we have free will to determine the course of our actions, but it may be, and it seems to have been discovered, that free will, which is operating locally, which we wish to operate locally, may in the end be superseded by bigger constraints of the whole system in which you operate. And I offer as an example of this Hannah Arendt's concept of the banality of evil, where evil resides essentially in the system as a whole. I think because of our desire to identify properties with small objects, this gets us into trouble. We're always looking for scapegoats, whereas in fact the system as a whole may contain the problems. So on this issue of the predictability of nature, there's this famous question that was asked by Edward Lorenz, who's an MIT meteorologist. Does the flap of a butterfly's wing in Brazil set off a tornado in Texas? And the translation of that is the cause of, it's not literally does that happen. In other words, should we expect to trace it? Rather, the translation is the cause of certain natural events indeterminate? The answer seems to be yes. And as I said earlier, it's probability, not certain cause and effect, that now dictates how scientists understand many systems, from subatomic particles to storms. And I think that this affects our relationship with the public. So the public, having been led to expect from science a series of ever more precise answers about the world we live in, the public, including many scientists, often don't grasp or appreciate the realms of uncertainty in which modern science is taking us. So science helps us to understand the universe, including revealing limits to this understanding. Some, such as Einstein, have argued that it is actually our ignorance, rather than the fundamental workings of nature itself, that demand these new probabilistic scientific laws. I'm not sure that there is a difference, but that's a philosophical question. It would be interesting to discuss. So this indeterminacy and so on has become interesting to us. We've gone down this route as scientists now because we can. I think that's a very common reason for things to happen in all spheres. So we can now deal quantitatively with unpredictability. Mathematics is being developed, particularly because advanced computational techniques and the actual the hardware, the computers themselves now allow us to do this. And so we have these new fields of nonlinear dynamics with attractors that offer explanations. These are not precise deterministic solutions, but sort of areas of behavior that can be defined by this sort of mathematics. Ideas like fractals and chaos, self-similarity, scale invariance, and all this sort of thing. And there's just a couple of examples there of the results of computer computations of the sort of thing that's now being used on the left here to study the behavior of the atmosphere and the ocean, the sort of work that was pioneered by Lorenz, who I mentioned earlier. And of course, the whole new area of fractals on the top right there. So, with that very long sort of introduction, this talk is really about complexity and complex systems-based understanding of nature and human society. So what I'm going to do is start with my beginning in the Earth system, where Martin said carbon, and just mentioning briefly, that's my departure point from this world of trying to understand the small details of what the Earth's made of, to making this leap into seeing the interconnectedness. So by studying carbon, diamonds, and small bits of rock, we make the leap to climate change, to past events in the Earth's history, and to a very complex picture of the Earth. So that brings up this whole topic of complex systems. And so I'll look a bit about structure and go into something about the structure of complex systems and about their evolution. And then get a bit to some of the broader applicability of this, which seems to be something that cuts across very widely. And then at the end, I mentioned briefly why I talk a little bit about some of the sort of theoretical aspects of it and finish with some conclusions. So here's where we start, what I've been doing for a fairly long time in my career, which is studying carbon in the deep Earth. And of course there's always the incentive to do this because of diamonds and knowing something about where they form and where they don't form and so on. And here's an example of a diamond that I found in my research strandloping around Kimberley. And this is a piece of rock that derived from the Earth's mantle beneath Kimberley by doing various things. We don't have to go into the details. We know something about the history of this. We know that it came from a depth of about 160 kilometers originally down in the mantle. We know that the diamond formed there probably somewhere around 3 billion years ago. There's some debate about that. And then this diamond was brought up by a kimberlite volcano to much shallower levels deposited in the crust about 85 million years ago. Big time differences here. And there it sat until the diamond mine came along and dug down about a kilometer where this particular thing was found. So that's sort of the history of that rock. And from this, we're able to start piecing together what is the role of the deep Earth, the whole planet, in the way that carbon moves through a planet. One of the things that has really struck great interest in the scientific community over the last 10, 20 years has been the idea that emanations from the Earth's interior can trigger biological mass extinctions. These mass extinctions have been well known for a very long time from people who study fossils and so on. And the most famous occasion has been to account for a mass extinction is probably the destruction of the dinosaurs somewhere around 65 million years ago, where evidence was found for a meteor, a huge meteor coming in from outer space and crashing into the Earth and releasing gases which changed the Earth and resulted in the death of the dinosaurs. But there's also a lot of evidence that that particular event coincided with a major volcanic eruption in what's now India, and this type of correlation has been found around the world. So, and the idea is that here are a couple of volcanic emanations here in southern Africa, nearby, a volcano that were the remnants of a volcano in southern Namibia that spewed a lot of carbon dioxide, and then the Drakensberg, the lavas of the Drakensberg, which themselves may well have carried a lot of carbon dioxide. Now, I just mentioned carbon dioxide here because this is not necessarily the agent that killed the mass extinctions that caused these mass extinctions, which are shown here down on the left. These peaks this is time and the extinction occurrence in percent. Now, extinction numbers or percentage of species or genera or families that die off. And those peaks are the major, you can see very sharp episodes where that has happened. And on the right is sort of the inverse of this, which is the global biodiversity as a function of time, with these sharp drops in it every now and then that have something to do with the release of gases from the Earth's interior, whether it's carbon dioxide or methane from sediments or something along those lines. So this idea that carbon dioxide in the atmosphere is causing big problems for life is, of course, something that we are now highly concerned with, given this observation here, which has now been going from late 1950s until the present day. These are the measurements of carbon dioxide in the air on the observatory on top of Mauna Loa in Hawaii. And you can see that from a first measurement at 315 or so parts per million, we're now at 404. That's a substantial increase. So something on the order of 30% or so. Known as the Keeling curve by the man who first started this. There's a picture of him there. And this, of course, has been known for many decades that this effect is liable to cause global warming. This was known long before this became controversial in any way due to political interference. But when we look back then at this has now prompted us, of course, to look into the changing Earth's climate, and we can now take this back. And when we look at the fluctuating Earth's temperatures back in time, we see, and we look on this top graph here. I'm not sure if you can make out those numbers, but this goes back to about the beginning of life, or beginning of multicellular life, of around 550 million years on the left. But the scale changes, because of course as we get closer to the present, our techniques get better, we have better resolution, and we can discern the patterns. But what we see is enormous wiggles and bumps and complexity. This is not something, there's something that's happening gradually, but superimposed on it are things that are happening all kinds of different time scales. Some of them seem repeatable, some of them come and go. And here's an example just from the last 800 million years, or 800,000 years, let's say the past million years. These are from the data from the cores drilled through the Antarctic ice cap. And here's in the blue, we have the carbon dioxide concentration variation, and on the bottom we have the temperature variations. And then, as I'm sure many of you have seen this, the so-called hockey stick curve on the right, there's a sudden leap above the dashed line to where we are now, being that massive increase in the carbon dioxide content of the atmosphere. So essentially close to doubling since pre-industrial levels. And this is, of course, what all the fuss is about. What I really want to get to is, and so we, of course, have set about trying to figure out exactly what's going to happen to us, and we've tried to take into account all these complexities that could cause all those bumps and wiggles that we see in the data. And this is the sort of thing you're faced with. I mean, this is sort of just part of it. So, I mean, you can see that it really doesn't make a lot of sense to look at this and say, oh, I ought to be able to make some simple calculation, predict what's going on. This is an enormously complicated thing. And so for this is one of the reasons why, just looking at the way the system behaves as a whole is going to help us a lot, I believe, in addition to our increased sophistication in dealing with the details. And so we have these two approaches that we're going to put on this together. And I don't in any way want to imply, especially from what I said before, that the way we've done science up to now is bad or stupid or anything like that. It's absolutely not. We've benefited enormously from it, and we'll continue to follow those practices and to benefit from it. But I think we've been missing something. So this leads us again into this whole idea of system. So what is a system? A bounded collection of interacting components, essentially. Nothing fancy. As an open system I mentioned earlier, something that exchanges matter and energy with its surroundings. And then what is a complex system? Well, that's basically, I don't know if there's any sort of really good definition of a complex system, but it's a system which, first of all, appears complex, and these are some of the phenomena that it exhibits: feedback loops, hierarchical structures, the capability to rearrange the components, in other words, to self-organize in response to either external or internal changes. So-called emergent properties, which are sort of things happening which you wouldn't have predicted from your knowledge of the components that go into it. Non-linearity, such as I've discussed earlier with respect to the nonlinear dynamics and so on. And here's a sort of illustration of a simple system, we might say a simple mechanical system or model system on the top. This is a complicated system where in both of these, nevertheless, the parts are fixed. They don't move in time. If something wears out, the engine stops and you take it out, you replace it with a new thing that looks the same. Over there is a complex system, the internet, something that's changing all the time, changing its links in response to whatever's going on. One of the most complex systems around, and one which of course influences us. So these, it turns out when we look at the physical characteristics of complex systems, there's some very interesting observations we can make about the physical character. Here's a number of systems that, not just biological systems, some of these are, the bottom ones are biological, the top three are not biological. You've got a river delta, got patterns of minerals on a flat rock surface in the form of a tree called dendrites. We've got lightning on the top right. So these systems all have these branching structures. They all have a sort of a similarity, and there's a hierarchy in these branches. You've got thick ones and you've got little ones, and there's all sorts of rules that people have worked out for these sorts of things. So there's something there that's common across the systems, and the big question is, what is it? Why are these things like this? We see that we can start, some people have started to see the Earth in this light. What seems to be the case is that those systems in the previous picture are organized to be efficient. They adjust themselves to those particular designs because those are the most effective designs for accomplishing what the system has essentially been built to accomplish. And this is perhaps one way that the Earth may have rearranging its tectonic plates in a similar way to certain convection patterns that are seen in synthetic systems called Rayleigh-Bernard convection. Now, this is what we find when we look at the behavior. So that was sort of just a few, one example of some structural similarities we see, which we can characterize and which have been characterized. But there's also some similarities in the way that these systems behave in very different systems. For example, here's on the top in red is a sort of a pattern of signals that emerge from somebody undergoing a brain seizure. In blue is the similar sort of pattern that emerges from earthquakes when there's a rupture in the Earth's crust. And when we do the sort of analysis, the statistical analysis of the power spectrum of this, you find that there are considerable similarities. And we find this across enormous systems, which have numbers, diversity of systems. Recently some very interesting popular books on this. We found that these same sorts of arguments apply to the stock market, organization of the stock market, and there's one particular man, Didier Sonnet, the author of that book on the top left, who's actually a geophysicist by background, who applies techniques that he learned in geophysics to be one of the major predictors and understanders of stock market crashes by using departures from this kind of behavior, this typical behavior, which he refers to as dragon kings, and which he says are expected events, as opposed to black swan events, which were also popularized recently, as sort of random massive events that are totally unpredictable. But as he shows, essentially those black swan events essentially lie on the continuation of the line that defines all events. They're just very rare events, a bit of the same distribution, whereas Dragon Kings are something different. So there's some now these sort of advanced quantitative statistical methods that are being applied to very practical problems in human systems. And we find that this whole trade now is developing of trying to predict the way that systems evolve and change, because what we find, as I mentioned earlier, is that there are sudden jumps. Now, in the picture on the left, there's a sort of a time series of some, it's a proxy, a geochemical. There's analysis of some component which we use as a proxy to indicate certain behavior, and it sort of fluctuates around, and then suddenly it jumps up and to another level. And this is very much similar to what happens when you boil a pot of water. When you warm the water up, and it sort of convects around and jumps around just like that, and then suddenly bubbles start forming, and the whole thing takes off and starts boiling. It goes into another system called a phase transition. And so, you know, so this particular one happens to be in the Earth's climate, and this is one of the big worries that we have now about, for example, if we mess things up enough that we start melting, say, the West Antarctic ice sheet, which is an enormous quantity of water that will then pour into the oceans. We can we can suddenly change the way that ocean currents work. We'll get back to where we are. So this is something to watch out for. And as a result, people like Scheffer, the author of this paper, who is an ecologist, has got into, he sees changes in ecological systems, biological ecological systems, studied that. As I say, here is on the right, bottom right, is an example from medicine where this sort of technique is being used to pinpoint potential onset of an epileptic seizure. And here we are back to Didier Sonnet and the whole issue of predicting of crises. And he has taken a pretty general view of this. And on the right is a list of all the things which he has listed in this paper that he wrote, and you know, characterizing this. There's power law distributions, and these are things that basically essentially follow the same sorts of distribution. So we have earthquake intensity, as I mentioned, landslides, the distribution of the size distribution of orbiting space debris in space, the area covered by forest fires, the sizes of rainfall events, as I've said, the returns on the Dow Jones Industrial Index, Hollywood movie revenues, the intensity of wars, the survival of identity theft losses, the sizes of cities, the patterns of acoustic emissions from stress materials, and as I said, brain seizures, heart attacks, and so on. And he's able to also look at what is it that causes these sudden departures from the sort of normal statistics, and he's able to characterize this in terms of, you know, particular way in which the bonds between the different components suddenly start strengthening as other things start to choke up, ready to pop and to change into something new. And that's sort of summarized in that diagram there on the left. So as we go forward, you know, so this is all very interesting, and it looks like there's a lot of great applications already happened. There's more potentially, but what exactly are these systems doing? I mean, they all behave the same. What exactly are they? What's driving them to be the same? Are they? People have proposed that they're optimizing something. For the technically minded, it might be entropy, or it might be flow of energy, or maybe minimizing something or other, but there seem to be some. So this is an area of very interesting active research and debate. And this And I find it very intriguing because in a way it's a sort of a search for new fundamental laws. That's the way some people have characterized it, certainly. Of course, these are not going to in any way contradict the laws of physics that we've already determined, but they may provide, there may be others there that are a function of systems behavior and not a function of sort of individual objects relating to one another. So here's some sort of speculation, just to finish off. Why is there complexity? Is it increasing? Well, here this is a picture of or a sort of representation of the expansion of the universe from its origins roughly 14 billion years ago, past the formation of the Earth about 4.5 billion years ago, present, and the universe, as we know, is flying apart, accelerating at an increasing rate, and this is believed by certain astrophysics, people in astrophysics, cosmology, and so on, to be a major sort of behind-the-scenes explanation for why things are sort of progressing in a particular direction. I mean, this is the sort of thing that's happened over time. We've started with star-forming regions, enormous dust clouds, and which then create stars, the bright spots, which then have matter condensing around them in solar systems. Tremendous structure developed out of essentially a great mess, and at the end of the day we end up with cities. You know, how on earth does this happen? And this is this sort of phenomenon of self-organization. And as I say, one of the ideas that's been proposed, and I had a slide in here about several other people, other ideas that have been proposed, but they were all proposed by white male Americans. And I thought, we've got to get some more ideas into this picture. Anyway, this one is also, Eric Chesson is an astrophysicist at Harvard, and he has come up with the idea that, in fact, you are looking at the energy rate density, which is changing with time. This is sort of the density, or the intensity with which energy is being processed, per unit time, per unit mass, and that is what is been increasing. On the top right diagram, you see this increase as we go from the galactic regime through to the sun, the Earth, plants, animals, and ultimately society. And here it's sort of shown with time the type of complexity that's happening. It's starting again with galaxies, stars, planets, chemical, biological, cultural, and so on. That's sort of a blow-up of that picture on the right. Just to also, in this particular picture, what's being shown is in the top right are the sort of evolution of human societies in terms of this flow of energy. And there are others who sort of take this approach as well. And the message here is that these same sort of phenomena seem to apply right across the board, and therefore they can be used right across the board. So I'd like to finish with this summary of the main ideas that have to do with the complexity and complex systems-based understanding of nature and of human society. First of all, as I said, the world is not necessarily deterministic, though it is in certain circumstances. The workings of nature and of ourselves, for we are not separate from nature, can be understood and in many cases require understanding in terms of complex systems, rather than in terms of the properties and the interactive mechanisms of the individual components. These systems, as we've seen, exist physically They seem to exist to enable flow, or as a manifestation of flow. In technical terms, they dissipate energy gradients, and they evolve with time. And the real big point about this is that flow and movement and change are much more fundamental to the way we ought to be thinking about our world. Even I'm talking about now when it comes to politics, when it comes to essentially anything. When it comes to lawmaking, for example, we make laws and they're immediately rendered useless by the advance of technology. I think we really have to go more towards principles rather than policies in the way that we seek to deal with many issues in human existence. And then, despite this diversity, which spans from the inanimate to the living, to the consciously willing, and apparently also to the abstract. I mean, it turns out that, for example, the words in the English language are also arranged similarly, could have appeared on Didier Sonnet's list. We see similar structural design, similar output patterns in time and in frequency, and ultimately may be governed by one or maybe more unifying principles. And so what I'm really hopeful for here is that we have a complex systems approach that offers a valuable framework for transdisciplinary understanding, and that many of these changes that the new science is indicating, and that people around the world are sort of leaning towards, partly I think in reaction to the way that science has tended to simplify and in many ways draw cartoon stick figures of the world around us. I think that people feel the innate need we need a picture that's more commensurate with the reality around us. So we take gratefully what science has provided in terms of all the things it's done for us, but we want to know something more about how the ordinary things around us really work. And what we find is that many of the insights that the new science is bringing are insights that have already existed. They've existed in the deep past. They existed in, for example, among philosophers in pre-Socratic Greece. They existed in Asia, China, in ancient India. And they exist in societies around the world today that are not Western in their outlook. And here in South Africa, a great opportunity where we have a confluence of essentially Western and a non-Western society with different ways about how the world works. And we're in a great position to put some of these things together. And I remember a talk given by a Native American philosopher when I was at Arizona State University, and he said that if the researchers in quantum theory had been Native American, they would have had much less trouble in getting to grips with the physical meaning and significance of what the theory was telling them, because in the Native American society, many of these concepts which were being forced unwillingly upon the scientists would have been quite acceptable and I would say obvious, but not a problem to envisage. So that the opportunity that we have here to now incorporate the way that other people see the world is of great value, and I think it has relevance to our current calls for some changes within the universities. We don't have to abandon the things that have brought good results, but we should certainly be opening our eyes more to these other ideas that have long been resonant in the societies. Thank you very much.